In this video, we're going to learn how to find the instantaneous rate of change of a function at a point. First of all, recall that the average rate of change of a function on an interval from a to a plus h is given by the change in y divided by the change in x. Now, on this interval from a to a plus h, we have that the change in y is just the difference in function values, f of a plus h minus f of a all over the change in x, and the change in x is just the length of the interval, which is just length h. So denominator here is h. So this here is the average rate of change. It's the rate of change of the function f over a duration of h. But what if we want to find the instantaneous rate of change? In other words, the rate of change at a single moment. Well, the rate of change at a single moment is really just the rate of change over a very, very small duration. So all we have to do is take the limit as h approaches 0. So let's write that down. To get the instantaneous rate of change, we just take the limit as h approaches 0 of that original difference quotient, f of a plus h minus f of a all over h. And the notation that we use to represent instantaneous rate of change is just f prime. F prime of a means the instantaneous rate of change at the point A. So this is our big important formula here for instantaneous rate of change. Why don't we go ahead and put it in a nice big box to illustrate how important it really is. The instantaneous rate of change also has a graphical interpretation. And to see this, first notice that the average rate of change is just the slope of the secant line through our point at A and another point which is a distance of h units forward from A. Let's go ahead and draw in that line. We'll label it as the average rate of change. Now, as we let the length of this interval go to 0, the point at a plus h approaches the point at A, and thus the secant line becomes closer and closer to the tangent line through the point A, which we'll draw here. So here is the tangent line at the point A. So this line here is the instantaneous rate of change. Great, so now that we know how to define instantaneous rate of change and interpret it graphically, this tangent line only intersects the graph of f of x at a single point, A. So its slope represents the instantaneous rate of change of the function f at the point A. Great, so now we know how to define the instantaneous rate of change of a function at a point, and we also know how to interpret it graphically. Now let's work some problems that actually involve computing this instantaneous rate of change. Here's our first problem. We want to find the instantaneous rate of change of the function f of x equals x squared at the point a equals 1 by computing the limit of the difference quotient. And that's just what we talked about on the previous slide. It's the limit as h approaches 0 of the change in y, which is f of a plus h minus f of a all over the change in x, which is just h. And remember, the notation that we use is we use f prime of a to label this instantaneous rate of change at the point A. Now here, the point that we want is the point a equals 1. So let's just go ahead and substitute in 1 for a. So f prime of 1 is equal to the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. And now it's just a matter of computing this limit. So let's go ahead and use the function definition. F of x is just x squared, so this is the limit as h approaches 0 of, in the numerator, f of 1 plus h is just 1 plus h, the quantity squared, then minus f of 1, which is 1 squared. And that's all over h. Alright, so we just go ahead and keep on simplifying. This is the limit as h approaches 0 of the numerator. Let's go ahead and expand out that 1 plus h squared. This is just 1 plus 2h, then plus h squared. And then we've got our minus 1 from the f of 1 at the end. And that's all over h. Now we see that some things cancel here. We've got a 1 and a minus 1 that cancel. So now let's go ahead and split up this limit. This is the limit as h approaches 0 of, first of all, we have our 2h term. So 2h over h, and then we're also adding our h squared over h. So we go ahead and continue simplifying. This is the limit as h approaches 0, and we see here that 2h and h, the h's cancel here, and we've just got 2, and then plus, in this other term, h squared and h, we can cancel the h in denominator, and then decrease this exponent by 1 to get just 1 in the exponent. So this is just really h to the 1, or just h. Okay, so limit as h approaches 0 of 2 plus h, we can just do direct substitution here. So we've got 2 plus 0 goes in for h, which is just 2. So there we go, there's our final result. The instantaneous rate of change of the function f at the point 1, that's f prime of 1, and we computed that that was equal to 2. So there we go, we're done. Now let's talk about another way that we can define the instantaneous rate of change of the function f of x at the point a. We know that another way of computing the average rate of change of an interval is to work just with the endpoints of that interval instead of factoring in the duration of the interval. So here we've got an interval with endpoints a and x, function values f of a and f of x. So the average rate of change on this interval is again just the change in y divided by the change in x, which is equal to the difference in y, so f of x minus f of a divided by the change in x, which is just x minus a. So again, this is the average rate of change. We can also use this definition of average rate of change to construct an expression for instantaneous rate of change. So let's go ahead and do that. Instantaneous rate of change. How do we compute that using this expression for average rate of change? Well, it's going to be very similar to what we did last time. Last time we said that the length of the interval here, which was h, needed to approach 0. The interval needed to get smaller and smaller. Now when we have our interval in terms of endpoints rather than a length of the interval, the way we let our interval get smaller and smaller closer to a is we let the right endpoint x approach a. So we just take the limit as x approaches a of this average rate of change f of x minus f of a over x minus a. And again, we just denote that as f prime of a, the instantaneous rate of change of f at the point a. So there we go. There is another big important formula that we can use for instantaneous rate of change. And we can use this to compute the instantaneous rate of change just like we used the other formula with h. Depending on the context, using one formula might be easier than using the other. So it's good to remember both of them. Alright, so let's jump into a problem. Alright, so here's our next problem. We want to compute the instantaneous rate of change of the function f of x equals 5x plus 1 at the point a equals 3 using the following definition that we covered previously. F prime of a equals limit as x approaches a of the change in y, which is f of x minus f of a, divided by the change in x, which is x minus a. In order to do this, all we really have to do is substitute in the point a equals 3 into this definition and compute the limit. So let's get to it. We have that f prime at 3 is equal to the limit as x approaches 3 of f of x minus f of 3 all over x minus 3. Let's go ahead and simplify this limit using our definition for f. So this becomes the limit as x approaches 3 of f of x, well that's just 5x plus 1, and then minus f of 3, so minus 5 times 3 plus 1. And that's all still over x minus 3. Simplifying, this becomes the limit as x approaches 3 of 5x plus 1, and then minus that 5 times 3 plus 1. 5 times 3 is 15, plus 1 makes 16, so minus 16, and that's still all over x minus 3. And we go ahead and keep on simplifying. This is the limit as x approaches 3 of 5x, and then plus 1 minus 16, that just makes minus 15. That's all over x minus 3. And hey, we can factor out a 5 from the numerator. So this is the limit as x approaches 3 of 5 times the quantity x minus 3 in the numerator. That's all over x minus 3 in the denominator. So we've got common factors, x minus 3 in numerator and denominator, that can cancel out. So this is just the limit as x approaches 3 of 5, and that limit is, well, just 5. So there we go, we've got it. F prime of 3, the instantaneous rate of change of the function f at the point 3 is equal to 5. That's our final result. So now we know how to compute the instantaneous rate of change of a function at a point using two different but equivalent definitions. In the future, we'll learn how this relates to one of the most central concepts of calculus, the derivative.